Okay, so this is E658 lecture 29. So we left off here yesterday where we discussed the motivation for using a design like this. It makes sense for voltage swing reasons to use one buffer which is an NMOS buffer, another buffer which is PMOS, and it makes sense to use a PMOS buffer which follows the whole capacitor rather than the other way around, because we know that in practice a lot of technologies are so-called N-well CMOS technologies where you don't have access to the body terminal of the NMOS transistor. It is naturally grounded, which means that the incremental gain from here to here is smaller than 1. So if you put the NMOS transistor here and the PMOS device buffer here, what would happen is that when this buffer is driving the large capacitive load here, the voltage on the whole capacitor will get perturbed simply because of some kind of Miller effect, because change by delta V, this will not change by the same amount, so some amount of charge will get sucked through that. And the motivation for using simple buffers like this is that these are probably the fastest circuits you can make because there is just one single transistor, and that's the situation. So unfortunately it turns out that there are several, while this is as fast as it can get, simplicity also means that there is not enough loop gain. I mean, there is all local feedback around. I guess all of you understand that a common drain amplifier is nothing but a feedback based voltage controlled voltage source. So, and its its DC gain is of the form GMRO by GMRO plus 1. So if you have just one single device, the RO you can get is basically, in this case for example, the RO of the current source, okay, in parallel with the RO of the transistor itself. Here on the other hand, it is RO in parallel with GMB, okay, and the output impedance of this current source. These are all small numbers, so which basically means that the voltage controlled voltage source action is not as close to ideal as you would like it to be, which basically impacts not only the DC gain being smaller than 1, it also affects linearity of the buffer, for the simple reason that you know that the output impedance of this current source, for example, does not remain constant as this voltage remains, please note that this is swinging a large voltage. V and P is jumping up and down, okay, by a large amount, which means that the quiescent voltage here is also jumping up and down by a large amount, and these are all nonlinear devices. So if you kind of look at the IV characteristics of the MOSFET, in a simple mannered analysis we say that it is kind of doing this, and then beyond this whatever VD-SAT, it is going off as a straight line, and all that is bogus, you know that, right? So that's just a model for us to analyze quickly. In practice, that thing, the slope of that line is varying with bias. So in other words, the output impedance of this current source is dependent on the absolute voltage here. For small signals, of course, the gain from here to here is some GM by GM plus GMB. In practice, all these are varying with signal, which basically means that the linearity of the small signal gain keeps changing depending on the value of the input. If the gain depends on the input, it is nothing but nonlinearity, so this causes distortion. So the same thing here, and if you want to maximize swing, you want to be able to swing large amounts here, which basically means that you would like this voltage to go as low as possible. If you want to swing large amounts here, you want to go as low as possible, correct? See, the maximum you can swing here is on the top limited to VDD, on the bottom, on the lower side, it is limited to, if this goes too low, then this will also go low, which means that this current source I1 will get into the triode region. So the limit is, you want to be able to push this voltage as low as possible in the interest of an increased signal swing. However, if you if you want, what is preventing you from using a very, very large swing is the fact that this will go into triode, and in practice you will find that there is no strict transition between saturation and triode. There is a gradual transition between the saturation and the triode regions, which basically means that even as this voltage enters that transition region of VDS between saturation and triode, you will find that the output of impedance of this kind starts to change from what it would be in saturation to what it would be in triode, which basically means that if you enter that danger zone, you basically, it will result in a lot of distortion. The same thing here, you ideally want this to go up as large as possible. Unfortunately, the higher you go, the more you will crush this, this current source. So the bottom line is that the linearity of this, this track and hold is rather poor. And most of this linearity is static in the sense that if I put 1 kilohertz, I'll get some, let's say I get some distortion. Even if I put 1 megahertz, I get the same distortion. In other words, most of the nonlinearity is memoryless. That's what the static nonlinearity means. And this is only one half of the, please note that we are going to be using fully differential inputs. So which basically means that this is the half circuit for the track and hold. This just processes the positive part. There is a copy paste replica which basically processes the negative input. So the input is V in P, V in M. The difference is what your input signal is. So there is a copy paste version of this guy who basically processes the negative output, and the output of interest, the output of the track and hold is not this voltage or V out M. It is the difference between those two voltages. So the question is, why is it? How do you know it's static nonlinearity? The intuition behind this is that these circuits are designed to operate at very, very high speeds. In other words, if this is working well, then the currents flowing through the parasitic capacitors must be much smaller than the other currents. If capacitive current is at any node dominates, that basically means that you're losing bandwidth. If you're operating well within the bandwidth of the track and hold, it means that currents through parasitic capacitors are small in relation to other currents, which basically means that things are okay. So one question is, why is this, how can you get better linearity? So if you want to take a lousy amplifier and make it linear, what would you do? What is the standard technique that you know? Negative feedback. So, and if negative feedback has to work, when does negative feedback really work? Negative feedback only helps you when loop gain is large. If you want to get large gain, what should you do? You have more stages, right? With one stage you can't get too much gain. So you cascade many stages and attempt to get gain, large loop gain, because that's when all the benefits of negative feedback become apparent. Which means that once you start cascading stages, you know that bandwidth goes down, you need to compensate and all this other stuff and kill bandwidth, right? So an op-amp based track and hold, for example, the flip around type thing that track and hold with an op-amp, right? You use an ideal op-amp, but if you use a real op-amp, you'll still find that it's quite straightforward to get, distortions of the order of, for reasonable swings of this order of magnitude. You find that it's not too difficult to get 10 to 12 bit linearity, right? So it just boils down to designing an op-amp with adequate gain. In a flash converter, it becomes impractical to do anything which is based on op-amps, for the simple reason that the more the transistors, the slower your circuit becomes. So, and flash by definition you build only when you're trying to really push speed in that particular technology. So an op-amp based thing would not be practical in this situation. That's the motivation for doing this thing. Okay. So now what happens if the track and hold has distortion? This is like a very exaggerated picture just to kind of drive home the point. So if you had an ideal track and hold, the input versus output of the track and hold would be a straight line. And what is the comparator array doing in this 3-bit example? What the comparator array is doing is looking at the output of the track and hold, comparing it against all these references. Input is larger than the reference, the output of the comparator is 1. If the input is smaller than the reference, the output of the comparator is 0, and then you have the usual thermometer to binary code conversion. So, for example, if the input lies between 3 and 4 delta, where delta is the LSB, in this example, the lower 3 comparators will fire, the upper 4 comparators will not fire, and the output code of the flash converter will be 3. Okay. So we made an error. The real input is between 3 and 4. It is some 3.1 or something like that, or 3.2. But the output is 3. but that is okay, that's what we bargained for. When we are designing an A to D converter, you know that you have to accept quantization noise. Okay, so you have only quantization noise when you have an ideal track and hold. Now, when you have a real track and hold, I have just modeled the, for the sake of this picture, I have drawn this grossly exaggerated curve. So the input versus output is no longer linear. So for the same input, for example, if the input was 3.2 delta or whatever, which was there in this picture, then the output is not the lower, the first three comparators don't fire because the input output characteristic of the track and hold is like this. If the input was this, the output in this particular example happens to be smaller than 3 delta. So only the first two comparators fire. So not only do you have quantization noise, you also have distortion, and you can see clearly that as the input becomes larger and larger, you need to change the input by a lot more around this region to flip one extra comparator as compared to here. I mean, that's basically saying that the slope of this curve is changing as you keep increasing the input. As we discussed, the larger you make the signal, I mean, you know, there's, linearity becomes a problem. So there's both quantization noise and distortion. Okay, so what would you do? The classical thing is to, if you have nonlinearity, correct, you have the input versus output is some curve like this. If you want sufficiently low distortion, what will you do? You know that if you take any nonlinear for this thing and then you focus your attention only around a small region, anything can be made to look like a straight line, correct? You just have to restrict you put blinders and then you look at only a small part of the curve, and even a spiral staircase will look like a straight line if you restrict your attention to a small section, correct? So which is equivalent to saying that if you restrict the input swing, if you make the input swing of the converter sufficiently small, then any track and hold can be made to look, linear. So you can say I have 90 dB distortion. There's no big deal. If I restrict the input swing to 1 nanovolt, then I can have the distortion will become 0, even if the track and hold is extremely nonlinear. The common thing used is that you design the track and hold, and then you find that if I make the input signal large, then there will be too much distortion, and if there's too much distortion, that's not good as far as the AD converter is concerned. So what I will do is I will restrict my swing. I'll go on increasing the signal swing, and I find that the distortion goes on going up. If I know that I'm going to be designing a 6-bit flash converter, for example, I know that the signal to quantization noise ratio can't be any better than about 37-38 dB. So if I say my threshold of pain as far as distortion is concerned is some number which is lower than that. So if we all agree, for example, that 45 dB is good enough as a THD number for the track and hold, then this 45 dB is about 10 dB lower than the signal to quantization noise ratio that you would get for an ideal converter anyway. Okay, so it's probably not too bad. So you go on, you design the fastest possible sample and hold you can, and you find how large a signal you can put in before the distortion becomes very, very bad. Okay, and then you say, okay, this is my peak to peak signal swing. And it turns out that if you kind of go scan the literature, you will find that a lot of these converters would tend to handle about a volt peak to peak differential in a 3.3 volt supply. And please recall that in a 3.3 volt supply, you're in principle supposed to get 6.6 volts peak to peak differential swing. Okay, but you only are able to do 1 volt peak to peak differential, and as you can see, this is a gross underutilization of the voltage headroom available. So a small, a small full scale means a small LSB size. A small LSB size basically means, okay, the random offsets in the comparators have to be smaller, but you know that the sigma of the offset is proportional to square root of device area. So if my signal swing was reduced by a factor of 2, to have the same performance, the sigma of the offset also has to go down by a factor of 2, which means the area has to go up by a factor of 4. So this basically means there is more participation in the comparators. The comparators have to be bigger, which means they have to be driven by the track and hold, which is a difficult thing to do. I mean, it's easier to drive C than to drive 4C. More clock routing, more power dissipation, and the bottom line basically means is that a small LSB size means increased power dissipation simply because the comparator array has to become larger in size. So there is a big motivation to try and say to operate the converter with as large an LSB as possible or as large a full scale as possible. Unfortunately, if you make the signals too large, we saw that our track and hold is less than ideal. So there is a fair amount of distortion introduced. So if one could somehow increase the LSB size and somehow get rid of distortion, okay, without using an op amp of course, then you could significantly reduce the amount of power that you burn, simply because you can now tolerate much larger offsets, which means devices sizes can be smaller, blah blah blah. And I have said, using negative feedback to linearize the track and hold does not work in an application such as this. So another idea is to do the following. So the problem earlier was the input-output characteristic of the track and hold was nonlinear, and if you recall the earlier picture, I mean, as far as the input-output of the ADC is concerned, if the input lies between 3 and 4 LSBs, how many comparators do you want to flip? The first 3 comparators must flip, correct? Earlier that was not happening because the references were all uniform, and the output curve of the input-output characteristic of the track and hold was nonlinear like this. So if the references were uniform, if in the last case, if the input was between 3 and 4 delta, we would find that only the first 2 comparators would flip. Okay. Now, what if the references were moved? By somehow, let's say we magically knew the characteristic of the track and hold. So if we went and pre-distorted the references by exactly the correct amounts, then in principle distortion can be eliminated. I mean, see, the flash converter is basically computing input by references. So the input is screwed up. So if you screw up the references in the same fashion, then everything will cancel out. And I mean, screwing up references is a very easy thing, in the sense that in principle the references are not processing any high speed signals. So you don't have to run anything at high speed, everything is pretty much static, so, and seems pretty innocuous, and you're able to eliminate distortion. So in this example, so what I would do would be to generate a set of nonlinear references, okay, and how do you generate, so what is the right way to pre-distort these references? The reference should go through the same kind of nonlinearity as the signal. So one way of generating the references would be to take the linear references, pass them through identical track and holds, and in this you exploit matching, because you know that the transistors on a chip could all be lousy. The transistors on a chip could be lousy, but if you built 100 of them, they would all be equally lousy, right? So you exploit matching and say, if I built 7 identical track and holds, they would all be just as bad. So if I took this set of linear references and passed them through these replica track and holds, you would get the outputs will be of the reference generator would now be pre-distorted in this fashion. So you can clearly see that the spacing between adjacent levels is decreasing, okay, and if the input is between 3 and 4 delta, clearly the lower 3 comparators will fire. If the input is between 4 and 5 delta, the lower 4 comparators will fire, and so on. So in other words, you have eliminated distortion, and you can now do this. This requires no high speed modifications at all. You can still continue to use your lousy nonlinear track and hold. Its only job is to do things fast, and you can now play around with the references and in principle eliminate distortion. So what issues are there? Okay, before we go there, you run a MATLAB simulation just to make sure that you're not deceiving yourself, right? So this is some track and hold that we designed, and we have linear references. You can see that not only this is all quantization noise. This is the third harmonic. Okay, and if you go and do the math, it turns out that the SNDR turns out to be 29.94, 30 dB or so. So you're losing basically about 8 dB because of this character here. Now, if you go and predistort the references by exactly the right amount, okay, it's clearly and you run the FFT, you find that the distortion is eliminated, and if you go and do the SNDR calculation, you will find that it is 37.6 dB, which is about what you would expect for an ideal 6-bit flash converter, right? I mean, there is no surprise. So nothing in the world comes for free. So let's see what all problems there are with this approach. Correct? It seems attractive, but let's see what the real problems are. Of course, one is that in a 3-bit example, we find that we need 7 extra track and holds. Okay. Now we know that if you make 7 extra track and holds, they're all nominally identical, but there's going to be mismatch between all the 7. And if a track and hold consumes power P, 7 track and holds are likely to will consume 7P. So not only is there, and this is how it is in a 3-bit example. So you can imagine what happens when you have a 6-bit example. So this is quickly turning out to be quite impractical. So one is offset and mismatch in these replicas, and the other one is power dissipation. These are the two problems. Okay. So how do you fix this? One thing you can exploit is the fact that references need not be refreshed every cycle. So what you can do is to use the same track and hold repeatedly, and you use that to predistort the references, with the understanding that at any one time you're going to be pulling out one comparator and storing the reference and offset on that comparator. You're going to be auto-zeroing that preamp one at a time, which means that the reference and the offset are stored on those input capacitors, and since charge is not lost from those capacitors, you can come back and do this for this particular comparator a long time later. There's no need to do this every clock cycle, which is something that makes sense even from a flash speed point of view, simply because that time is now available for conversion. So before I go to the details, this is the comparator, same old stuff. The advantage of using a comparator like this rather than something with simplified clocking is the fact that the dynamic offset of this comparator, as you've seen in your assignments, can be a lot smaller than what would happen in a whole bunch of other comparators, where the two regenerating nodes are either connected to VDD, they begin their life at VDD and then regenerate. So there's a big change in the common mode voltage, which causes a large amount of dynamic offset. Okay. This one, on the other hand, you can start off at pretty much the magic voltage of the latch, and the common mode jump is very small, which causes very small dynamic offset. And this is the preamp. Again, you know this stuff. So these are the two references. These are the two inputs. So during the special phase called the auto-zero phase, disconnect the preamp from the latch, you put this in auto-zero. These capacitors CC, okay, store not only the references, they also store the offsets. A little bit of calculation based on the leakage currents of these switches will show that you can hold this charge for several milliseconds. Okay, and this is the comparator, this is the preamp, this is the latch, and during the auto-zero phase, the preamp has to be disconnected from the latch. So this LC, which connects the preamp output to the latch, is ANDed with the control signal for this switch is ANDed with auto-zero bar. So when this comparator is being auto-zeroed, these switches are open all the time. So what do you think will happen to the output of the latch? If you take a latch, if I get rid of this entire part, nothing prevents me from clocking the latch, correct? What do you expect the output to be? See, during the latch reset phase, you're bringing the two together, and then you regenerate. In principle, it seems as if it should stick there, right? Because the two voltages are being charged to the same amount. But that's, that it is unstable equilibrium, and there's going to be a mismatch anyway. So the output of the latch, when it's not connected to the preamp, it will be a random, either a 1 or a 0 depending on mismatch here. That's all. The only thing to be aware of is that the output of the latch has got nothing to do with the input. It's got no correlation with the input whatsoever. During the AUTOZERO phase, this whole comparator, the output of decision of this comparator is some random thing, which could be either a 0 or a 1 with equal probability depending on the way these things are mismatched. But the key point to note is that that decision has got no bearing. From that decision you can't make out anything about the input. Okay, you're getting a logical one, but it doesn't help you figure out the input. Right, so this is I kept saying in the class, the AUTOZERO in this particular implementation runs in the background. In other words, the user doesn't know that all this management is happening in the back. So what do you do about this? So when you're AUTOZEROing a comparator, it is unavailable for conversion, right? And the output is some random output. Now the question is that completely screws up our ADC performance? Then obviously this is not a workable solution. Okay. One thing you could do, for example, is the following. When this guy is out of action, you have one extra comparator. You know that you're going to pull this guy out. Okay. So you charge up the references to that comparator before you pull this guy out, and then replace that electrically. Physically you can't replace anything because this is all laid out, right? It's all hardware. Okay. So electrically it's, you must somehow disregard the decision made by the comparator which is being AUTOZEROed, and instead use the decision made by the spare guy, and then everything remains. So unfortunately that's while that sounds very nice, in practice, please note that the substitute, okay, must substitute for comparator 1 for some time, it must substitute for comparator 2 for some time, etc., all the way up to 63. This is a 6-bit flash converter. So which means that wires must be running from the output of the substitute to all the 64, correct? So that's clearly a difficult thing. So the problem with having a single substitute is that this excessive amount of wiring that goes on, that needs to go on between this extra substitute and all the other 63 players. Then another argument is, okay, then you don't have you have one substitute for every player, correct? So then there's no wiring, right? So each substitute has been trained to basically play like how the other guy would, and so then you put these two guys side by side and there's no difference in wiring. What is the problem with this now? It is twice the area and twice the power. So the best thing would be to somehow avoid having to use this substitute altogether. This is what we do. The motivation behind this is what I just told you, right? So let's say the input was here. Okay, these are the comparator numbers and their references. If the input is here, then if all the comparators were competent and able, then the outputs would be a thermometer code all ones and then a 0, and all zeros following this, and then everything would be nice. Let's assume that a comparator far away from the input is being AUTOZEROed. So the output of this comparator is, if this is being AUTOZEROed, the preamp is being pulled out and the latch makes some random decision. So it could be either a 1 or a 0. So if this was a 1, then there is no problem at all, right? Because this is still a nice thermometer code and there is no issue. If on the other hand this turned out to be a 0, you know that this is a spurious thing, correct? So this is like so-called bubble in the thermometer code, and it's very straightforward to simply eliminate the bubble by majority logic. So the bottom line is that if the comparator being AUTOZEROed is very far away from the input, then there is no problem at all, because the output is going to be a bubble, and that can be simply eliminated by majority logic, and I get a clean thermometer code and there is no problem. Okay, The problem only comes when the input is close to the comparator being auto-zeroed, and if you go and do this analysis, I mean, you go through the flow through the logic, you will find that if the input is close to the comparator being auto-zeroed, the error, once you do this majority logic, is not simply the quantization noise epsilon, but either can be 1 LSB plus or 1 LSB smaller. But most of the time, with a large probability, the input is far away from the comparator being auto-zeroed. The input is here. Okay, you could be auto-zeroing any one of those comparators. So if the input and the comparator, the auto-zero sequence are uncorrelated, which means that one doesn't know what the other is, then with a large probability, the input and the comparator being auto-zeroed are very, very far away, which means that if things are very far away, you know that there is no problem at all. You just know that this guy made a mistake, use majority logic and be done with it. If on the other hand the input is very close, then you make an error. Okay, the usual quantization noise would just simply be this epsilon, which is the difference between the reference and the input. If the input is very close, you can go and do the math, and you will find that with this probability of 1 by 64, the error, quantization error jumps up to delta plus epsilon, and with this 1 by 64 probability, the quantization error goes to minus delta plus epsilon. So ideally the variance should be delta square by 12, but with this kind of distribution, it is not delta square by 12, it should be larger. If you go and do the maths, it turns out that this is about, the peak SNR is about 1.38 dB, smaller than what you would get for an ideal 6-bit flash. This is what you would get for a uniformly distributed input. Clearly, I mean, this for a sine wave, I mean, this loss should depend on the PDF of the input itself. I mean, a sine wave, please note, spends a lot more time at the peaks than at the zeros, which means that you will get, it's very likely to occupy these two peaks. So if the comparator auto-zero, being auto-zeroed is there, then you'll get more distortion at the peak. So for a sine wave input, it turns out to be 1.5 dB. Okay, but 1.5 dB itself is quite a small number. I mean, typically what happens is that you will design a 6-bit flash, but if you get an effective number of bits after you build it because of DNLI and all that, the quantization noise will go up. There will also be distortion because of the track and hold not being as ideal as you would want. Okay, bearing all this in mind, it turns out that a practical converter will have, if you get 5 or 5.2 effective number of bits, then you are actually doing pretty well. So if you lose 6 dB, over the entire range in the worst case, nobody is going to, yell at you, right? So to begin with, this 1.5 dB is small, but it turns out that you can actually do better than this by observing the fact that the comparators can hold their references for several milliseconds. Okay. And this converter was running at 160 megahertz. So in other words, period available for conversion is about 6 nanoseconds. 6.25 nanoseconds is 160 megasamples per second. So this is a 6-bit flash converter intended to operate at 160 megasamples per second. Based on simple math, it turns out that the capacitors which hold the references and the offset can hold on to that charge for several milliseconds, which corresponds to several milliseconds is 10 power minus 3, nanoseconds is 10 power minus 9. Okay, so they can hold on for several, almost a million cycles. Okay, so you can auto-zero a comparator and come back and auto-zero it a million clock cycles later. So in other words, once you've finished auto-zeroing all the comparators, you don't have to auto-zero again for a very, very long time. And if you're not doing any auto-zero here, you're not removing any comparators out of the array. So this behaves, in this period, behaves like an ideal flash. In this period, there is that SNR loss because of pulling comparators out. So if you do them, and it turns out that it's quite easy to make this 99 times this. 1% of the time is when you're auto-zeroing. So during 1% of the time, we have a small reduction in SNR. during the rest of the time you have no reduction in SNR, so you go and do the math and you will find that the losses can be brought down to virtually nothing. Here, I mean, the advantage of doing this rather than have substitutes and so on is that you are not doing anything hardware wise, you are not doing anything out of the ordinary. Everything looks pretty normal and which is what you would do in a regular flash ADC anyway. You would use bubble correction to correct one bubble, and everything else remains the same. So this is the block diagram of the flash. These are the 63 comparators. This is the majority logic. This is the thermometer to 1 of n decoder, and this is the final encoder, which takes this 1 of n code and generates a binary output code. There is a clock generator to generate the myriad clock phases required for all these layers of logic and the preamp and the latch and so on. And now you want to pull comparators out and AUTOZERO them, correct? So you need to have some kind of counter which will select which comparator to pull out. You need to have a nonlinear reference generator. In other words, you need to have a reference generator which generates this, not delta 2 delta and so on, but this delta 2 delta and so on pass through a track and hold, so that the outputs of this reference generator are pre-distorted exactly the same way as what the input would get screwed up by this main track and hold. So this is the detail of the reference generator. So this is the 6-bit resistor string which is used to generate the linear references. So you know that you want, let's say you want to AUTOZERO the 34th comparator, then this will read 34. So the 34th preamp, is pulled out of in principle pulled out of the array. So the AUTOZERO switches are closed around there. The code 34 is given to this string of resistors. So you will tap off using a mux the output of the 34th resistor. That goes to a replica track and hold. For the replica track and hold, you don't need the switches at all, right? You can eliminate the switches completely. So this is nothing but an NMOS source follower followed by a PMOS source follower. This output goes to that particular preamp which is being AUTOZERO. And this is not varying with the signal. This is a very slow thing, right? So this output has to be connected to all the preamps. And I mean, this is like a bus which runs across the entire comparator array. Particular preamp which is being AUTOZERO'd, when it is told to AUTOZERO, it will sense the voltage on the bus and AUTOZERO itself to that reference. And so as the count keeps going from 1 to 64, the output here at A is a ramp like this. I mean, not a ramp, it's a series of steps, alright. And because this is nonlinear, the output at B is something like this. So if I kind of zoom in there, you can see that this takes uniform steps, and here these steps are non-uniform because of they have been predistorted by the replica tracker. Please realize that this comparator array is a physically long thing. There are 64 comparators like this. So, and you know that if there is a gradient of resistors, as you have done in assignment 3, you will pick up distortion because the change in the LSB is not the same, okay. But now here only one reference is being accessed at a time. So in principle you don't need to run this as an array. So all this can be laid as a square, small square, thereby this issue of gradient across the chip doesn't arise at all. You prevent distortion of in the ADC caused by gradients of resistivity along the chip. And you can see that there is virtually no overhead, power wise for distortion, cancellation, simply because all that you have is you would have had to have the resistor string anyways. You would have had to have the bubble correction anyways. The only extra is the small replica track and hold, and this can be a scaled version of the main track and hold. The main track and hold you need to burn a lot of current because it has to charge up a whole bunch of capacitors. But this can be very, very slow. So the power dissipation in this, I think in our implementation was like 1/16 or something of the main track and hold. So the power dissipation extra overhead that you pay to cancel distortion is virtually 0. So you're basically ending up with an A to D converter which can, now since you know that you can cancel distortion, you go crazy and say, what? Jack up the signal strings as much as possible I mean, so once I increase the signal swing, you know that I get a whole bunch of benefits. So I know I have a technique to kill distortion. I can go overboard and do whatever it takes because I know that anyway it's all going to get cancelled. So thanks to this technique, you're able to increase the nominal ADC input swing from what typically is 1 volt peak to peak differential to 3.4 volts peak to peak differential. No, but please note that this is it is not, first it doesn't have to swing rail to rail, correct? Because every step it's only jumping up by 1 LSB, okay? So the amount of current that this needs is very, very small, and the AUTOZERO phase itself is very large. So in our this thing we actually AUTOZERO, the time for AUTOZERO is actually 4 clock cycles. So in principle, so this doesn't have to have any current at all, okay? First of all, its output swing changes by by 1 LSB every 4 cycles. So when compared to the main track and hold, which in principle has to swing full scale in 1 cycle, because Fs by 2 is the Nyquist tone. Bandwidth wise, this can be a very low bandwidth effect. This is the test setup. So this is the clock, this is the sine wave source, this is a low pass filter to basically filter, I mean the sine wave source and the clock are synced together, because you know that otherwise if the two are not synced together, then there will be FFT leakage when you do the FFT, right? So, and you are able to set up these clocks such that prime number of cycles, all this stuff is this thing. There is a low pass filter which cleans up. The sine wave source is supposed to be sine wave, but it has harmonic distortion of its own, which has to be cleaned up, otherwise you will mistake the distortion of the source to be the distortion of the ADC. So you put a low pass filter, and this is what is called a Bal-Un. So all these measurement equipment are single-ended sine waves. You have to convert them into a differential output. So this is nothing but a center tap transformer which takes a single-ended input and generates a differential output. And then we have some knobs to play with. You can run AUTOZERO whenever you want, okay? And we could disable AUTOZERO for a long time if we wanted to figure out how long it would take before the ADC would get screwed up because of leakage from the capacitors and so on. This is the logic analyzer, alright, and then you do FFT from the data grabbed from the logic analyzer. This is an FFT. This is being clocked at 160 megahertz, so the Fs by 2 is 80 megahertz. The input tone is around 20 megahertz, and you can see that the third harmonic distortion is around here, is about 40, the third harmonic distortion, and this is for a full scale input signal, okay. So you can see that the distortion compensation is working quite well. And this is the measured signal to noise plus distortion ratio as I go on increasing the input frequency. One thing you can see is that for low frequencies you are doing very well, in fact, right. So the signal to noise plus SNDR is like 36 and something dB, and as the input frequency goes on increasing, you generally expect circuits to performance to get screwed up a little bit. So this is also not unusual, okay. This is the so called discontinuous background AUTOZERO mode, where you AUTOZERO for some time and don't AUTOZERO, wait for a long time and then you AUTOZERO again, and we saw that the degradation in SNR is very small, okay. Here is when you continuously AUTOZERO, and doing the math we found that the difference between the two should have been about 1.5 dB, right, which is kind of, and so this is the, I haven't shown the DNL INL here, but the DNL and INL peak is about 0.35 LSB. This is in a 0.35 micrometer CMOS, which is a factor of 4 slower than the technology that you guys are using in your assignments. The power dissipation is 50 milliwatts, and the dynamic performance is, the equivalent resolution is 5.3 effective bits at Nyquist. In other words, the equivalent resolution of an ADD converter is defined as the SNDR you get minus 1.76 divided by 6.02, okay, and this should be done for the Nyquist tone, Fs by 2, not at DC. At DC, as you can see, you can do much better than what you can do at Nyquist, and the figure of merit of how efficient an ADD converter is, a flash converter is, for example, is the so called energy you consume for every level that you resolve, okay. So it turns out that this is 1.9 picojoules per level, and you can then put this in comparison with a whole bunch of other data converters that have been reported by in the solid state circuits journal over the years, and you can see that the this one by Unlock Devices is a good state of the art converter, and they run in the same technology. They run at 1 volt peak to peak differential swing, and you can see that the power efficiency is about 21.9 picojoules per level, whereas we are doing much better than, simply because you are able to, and it's not a factor of 5% or 2% better, right? You can see that there is a significant difference between the two, and that can be attributed to the fact that you are using large sequence mix. Okay, so this is a proof of concept of an idea that you have, and you make silicon, and so bottom line is that